Hello, here's a quick video for the Centripetal Lab. What you're going to need, your little rubber stopper. Got holes in it because you're going to thread some string through it. String, I've unwound mine because I was playing with it. This little plastic straw tube, but plastic straw would work, but a more rigid plastic tube is better. Little paper clip, and then a bunch of these little washers. So what you're going to do first is weigh all the washers and then divide by the number of washers to get your average weight per washer. This is better than individually labeling every washer and then weighing every washer and knowing, oh, I used washer 1 through 4, so this get the average of every washer. Then if you use 5 washers, it's 5 times the average. You could also individually weigh them per run if you want. Anyway, you need to get the weight of these washers because what we're about to set up, there's going to be these washers hanging down that's going to have a gravitational weight of mg, and where m is the weight of the washers, or the mass of the washers. Should be using mass there. So what you're going to do is take your string, thread it through the straw, and then on one end tie the rubber stop. So here I would cut my string, tie the rubber stop. I'm not putting my rubber stop on here because I'm in a kind of a tight area and I don't want to be swinging a lot of mass around. So for my little demo right now, we're going to imagine my rubber stop is tied here, which really is a little daft, but here we go. Rubber stop tied to one end, and then on the other end, you can tie the paper clip and then put washers on the paper clip, or put washers on the string and then tie the paper clip, which is safer so the washers can't sling off. But you'll put some washers on the bottom. So I got 2 on mine right now. So now I have straw, string with washers and paper clip. Then on the other end I have my rubber stop that's tied, supposedly. So there we go. We got this side set up. So what we're going to do, we're going to spin this above our head like a helicopter to a speed that this hanging mass, let me shorten my string here. So we're going to spin this above the top here, above our head, and it'll look a lot easier when I do it here in a second, at a speed that this hanging mass doesn't drop or come all the way up against the straw. So we need to find a speed that this mass is in equilibrium, we'll say. When that happens, this hanging mass will be this force will be the same force as this centripetal force that we get from spinning around. So I'm going to try to do this here, my little setup. So it's easier to use your dominant hand to try to spin this. Pinch the string, get it spinning, and then release it. And then move your hand down. So now I'm spinning my little rubber stop above my head, a little helicopter. So this is my little helicopter blade. And there's a centripetal force now going around that's pulling this weight through the straw. Okay, it's hard to point and spin at the same time. So this should be going, just looking pretty still. Let me get this going. So you can also hold this with your offhand and spin it real fast, and you can feel that this thing is trying to sling up. It's just like, I don't know, you ever spun some kind of ball and have a string before, but it's an interesting feel. So you find it at that right speed, get the speed, and then get it going, and then you or yourself can time 10 revolutions. So I want to start timing. Whoa, I went too slow there. I want to start timing whenever it's in front of me, and then go. 1, 2, 3, 4, 5, 6, 7, 8. And this is about a second per revolution here. And then get to 10 and stop the stopwatch. And then also try to know where you were spinning. So before you stop spinning, try to pinch it off, because you're going to measure this radius. So from where the plastic straw was as the center of our little circle of motion here, you'll now measure this radius from my right hand, my right hand on the screen, to my left hand holding my rubber stopper. So we'll say that's about 2 feet. So you'll be in centimeters and meters for physics, but just eyeballing this without using a tape measure right now, we'll say 2 feet. So you get this radius, then you get the average time per revolution spinning it. So let me share my screen. All right, so here we go. So that's all I'm just trying to show. Here's a circle of motion. There's a little rubber stop above my head. Here's the radius that I said was about 2 feet. And then here is the weight hanging. Here's some sample data since it's already pulled up. You'll start with the radius. Here they got about 0.6 meters. Time it, get the average. Here's the average. From the radius, you can calculate the circumference. They also give you this formula here to calculate the velocity. V is 2 pi r over t, or c over t. So you got c, you got t, you can get v. Once you got v, you can calculate fc, which is whatever the moving mass was. So you actually got to weigh your little rubber stopper. V squared you just calculated divided by r, which you just used. That's your fc. And then Fg is the gravitational weight of, or gravitational force of the hanging washers. So in my little sample movie I just did, or demo, I just had 2 washers. So my M would be 2 washers worth of weight or mass, and then times G. The G is kind of hidden here, but whoa, you can see it's F equals mg. So there's G, 9.8 meters per second squared. With the 2 different forces, you can calculate a percent error, and you can see this isn't the easiest and cleanest lab. So when you get to the smaller radius, it gets easier, or you get better percent error. That's it for that exercise. Exercise 2 is a simulation, so I'm not going to spend any time clicking through the simulation. Just follow the steps. It should be pretty simple. If not, send me an email. But that'll do it. I want to get off this one and make another one.